Real-world scalable entity resolution. Hi, I'm Nick Bates-House, Chief Architect at Tamr, and this is part 3 in our 5-part series on entity resolution. In part 1, we talked about why entity resolution at scale is hard. We talked about algorithms, imbalanced classification, and other challenges that are hidden inside this entity resolution problem, and looked at some measures of success, including being able to run entity resolution on 500 million records representing the entire population of the United States in under 3 hours for under $300 on commodity hardware. We also looked at fast deltas, being able to process a 1% change in those 500 million records quickly and with stable IDs. In part 2, we looked at the easy part and making the easy part cheap. We looked at pre-grouping, feature extraction, and blocking as techniques to reduce the magnitude of problem that we need to apply machine learning to directly. And as a measure of success, we observed that we turned those 500 million input records for the US population into fewer than 1 million pairs. In part 3, we'll look at what happens next, which is the hard part, and making the hard part scale. We'll start with some definitions. What does it mean to be hard? What does it mean to scale? We'll look at the data processing workflow, and again, look at some measures of success. So what does it mean to be hard, and what does it mean to scale? What is hard is that the standard entity resolution workflow is very sensitive to inefficiencies, and at large scale, those inefficiencies really get multiplied. Our data processing workflow is going to cover 3 different things, each of which multiplies any inefficiencies in our algorithms. First, signals. This is column-wise measures of similarity between 2 records. And the input to signals is the number of pairs times the number of columns times the number of tokens per column, and if using bigrams, multiplied again by the number of bigrams. At the scale of 500 million records or 1 million pairs, any inefficiency in our signal algorithms, in our signal computation, gets multiplied manifold. Once we've computed signals, we need to compute record-wise similarity. This is where we apply the machine learning model. And that machine learning model input is the number of signals times the number of pairs. So that's roughly the number of columns times the number of pairs. So again, any inefficiency in our machine learning model is multiplied manifold. Finally, we're going to compute clusters, and a clustering is an iterative distributed self-join whose input is magnitude the number of pairs. So any inefficiency in our clustering algorithm is again multiplied manifold. That's what is hard. How do we know if we scale? We scale if we have efficient evaluation on large-scale data. And this efficient evaluation is generally measured best in dollars. How many dollars does it take to complete a run in a timely manner? And then we also want to distribute evenly on commodity scale-out infrastructure. Distribute evenly means that we should see a nice clean curve as we increase the scale of our scale-out infrastructure. We should see the time rein in proportionately, and hopefully with only a reasonable change in the dollar cost to running on a larger scale. So that's what it means to scale. Next, we'll cover the data processing workflow for the hard part. In part 2, we covered the first 4 steps in this data processing workflow: pre-grouping, features, blocking, and pair generation. In this part, we'll cover signals, similarity, clusters, and we'll also add on record consolidation at the end. Survivorship we will cover in part 5, handling change. The first step in our workflow is computing signals. Keep in mind that the output of the easy part was a bunch of pairs. We have 1 million pairs for our 500 million records. For each pair now, we want to look at each of the fields, each of the columns that is interesting to machine learning, and compute a signal, which is a per feature similarity metric. For text, as we've mentioned before, we want to use IDF-weighted normalized cosine similarity. We have already captured those IDF weights off in a separate table. Those can be joined back on. For numeric fields, we want simple difference, or we can scale that difference by the maximum of the 2 values in order to get a relative difference. And similar for geospatial, we can either use discrete Hausdorff distance, or we can use that discrete Hausdorff distance divided by the maximum diameter of the 2 geospatial features in order to come up with a relative distance. We provide a nice user interface to our users, showing them what's going on here, where they can see individual signals with highlights showing when values are actually identical. We then aggregate those signals into per pair similarity. This per pair similarity metric is computed by a machine learning model. The machine learning model is going to look across all of the individual signals and come to an aggregate decision about whether the two records in a pair are a match or a non-match. For this, we're using a random forest, and in part 4 of this series, we'll go into the details of what that random forest is. One of the key concerns with using a classifier like a random forest to make this match or non-match judgment is that a decision tree, random forest being a kind of decision tree, really just comes up with a match or non-match judgment. But for clustering, we want a similarity metric showing the degree to which the records in the pair are similar. For that similarity metric, we open up the random forest and we look at the submodel disagreement, and we come up with two separate metrics. One metric is a straight probability, which is the fraction of trees that predict match. That gives us a probability of match that ranges from 0 to 1. And then for clustering, and in particular intra-cluster and intercluster confidence metrics, we're going to use 1 minus the entropy of that probability as an information metric. So that's how we derive per pair record similarity from the per pair signals, which are the per feature similarity metrics. Once we have those per field similarity or per feature similarity metrics, and we have the per record similarity metrics, we have a bunch of pairs that link up different records in that 1 million record or that 1 million pair space. We now need to assemble those into clusters. And for clusters, there's a first step, which is computing connected components, where we take those pairs and we link them together into this undirected graph of records, where each pair is an edge between records and each record is a node in the graph. And then we can use a relatively standard algorithm to assemble the individual records across those edges into clusters, where each cluster observes some metric. And that metric we're using is average linkage. We want average linkage within the cluster to be above 0.5. There's a standard algorithm for doing this, WPGMA. Unfortunately, it is complexity big O of e squared log e in the number of edges within a connected component. Even worse, it only parallelizes by connected component. You can't parallelize within a connected component. We've developed a sort merge based variant of this algorithm, where we first sort the edges and then we're able to merge clusters in priority order by that similarity. So the sort merge, because it's a sort, it's e log e in the number of edges. But most importantly, we can achieve near perfect parallelism by distributing the work within a connected component. So with that, we don't need to worry very much about the skew in the size of connected components. We're able to distribute evenly. And then we have an efficient clustering algorithm where we're able to compute these clusters and resolve conflicts in the pair space. What is a conflict in the pair space? If you look on the left-hand side, you'll see, for example, record 1 forms a pair with record 2 with a similarity of 0.7. Record 2 forms a pair with record 3 with similarity 1.0, but record 3 does not form a pair with record 1. They didn't pass, that pair did not satisfy any clause in the blocking model, so the similarity between those two is 0. So you would think that similarity would be somewhat transitive, that because record 1 is similar to 2 and 2 is similar to 3, that 3 would therefore be similar to 1. What we see in the pair space is that it is not similar, and that's a conflict. Clustering resolves those conflicts. So you can see on the right-hand side, records 1, 2, and 3 are assembled into a single cluster. Record 4, which is similar to record 3 but not to record 1 or 2, has been placed into a separate cluster. So clustering is resolving those conflicts. That gives us a really nice machine learning oriented output of clusters, but there's a challenge here. Those machine learning clusters are probabilistic. And some things require determinism. In particular, regulatory and compliance may have deterministic guarantees that must be made in the data. A great example of this is when doing patient mastering. Two patients with different patient identifiers cannot be considered the same patient. They might have different blood types, and treating a patient with one blood type according to a different blood type might be a fatal mistake. So we need to have patients with different patient IDs rigorously separated deterministically. Having a rule-based system is a great way to provide determinism, but at scale, those rules become unmanageable. So rather than having a pure rule-based system, we allow a rules overlay on top of the machine learning clustering. So we still use machine learning, which can learn by example. It's able to get those interesting cases correct where the information is diffuse across the pairs. We have pre-grouping that gets the obvious match cases right. We have blocking that eliminates the obvious non-matches. Now we need something to overlay on top of the machine learning clusters in order to provide these guarantees in addition to the hard work that the clustering has already done. The way that we've done this is we allow the user to provide a list of simple rules, and those rules will be applied on top of or in addition to the machine learning clustering. So the rules do not need to get everything right. They just need to specify what are the guarantees that we need on the clusters in addition to all the work that the machine learning is doing. So one example of this is for organization mastering. If an organization has a DUNS number and a parent DUNS number, then two records that have different DUNS or different parent DUNS must be placed in different clusters. Two records, conversely, that have the same DUNS and the same parent DUNS must be placed into the same cluster. These are simple rules, relatively easy to understand. We provide a framework that applies these rules in strict order. But this is in addition to the machine learning. So organizations that lack a parent DUNS or lack a DUNS or lack both can still be clustered together, and these rules will be applied on top of that machine learning clustering. And the complexity of applying this rules overlay is n log n. That's n log n in the number of clusters. Finally, consolidated records. The output of clustering itself is useful for many applications. That is linkage information. We're taking records from potentially many different source systems and linking them together so that we have the primary keys from those different source systems related by the cluster that they've been placed into. In addition to that, people also often want a view that is a single record representation of an entity. That is this consolidated record. We're going to consolidate all of the information across all the records in a cluster into a single record. The model here is per column rules. These rules can be evaluated in parallel by cluster. This whole thing is n log k, or k here being the number of records per cluster. We provide a facility for subject matter experts to specify high-level rules. These high-level rules are able to express or capture constraints along the lines of address and city must come from the same record. I can't pick an address from one record in the cluster and the city from another record in the cluster because there's a risk that that address does not exist in that city. I also want to express things like source priority, data recency, those kinds of things. So that covers signals, similarity, clusters, and record consolidation. What is a measure of success? How do we know whether we've done this well? Well, the first way we know that we've done this well is what we covered in section 1, which is we're able to perform entity resolution on 500 million records representing all the people in the United States of America in under 3 hours for under $300. But we also have demonstrated near perfect parallelism, where if you look at the change in environment size, we see that scaling that environment from extra small to large maintains a relatively stable cost per run, while the test duration scales smoothly according to environment size, with the extra small taking about 4 times as long as a large environment. And this is by environment rather than cluster size, because an environment here is not just the size of the compute cluster, it includes also the size of the storage cluster, the network that's configured, the node type, etc., so that the entire cluster is tuned to work together. But for the duration of the run, we accrue all of the charges across all the different pieces of that environment, total all those charges, and you can see that the per run cost is relatively steady at about $300, while the runtime is decreasing. This shows that we are efficiently using the additional scale-out resources available in those larger environments. That's the end of part 3, how to make the hard part scale. We covered signals, similarity, clusters, and consolidation. And as a metric of success, we showed that we're able to run entity resolution on those 500 million records in under 3 hours and under $300, and that we have achieved near perfect parallelism. I'm Nick Bates-House, Chief Architect at Tamr. Join me for the next part where we talk about effective learning.